Okay, guys, hello and welcome. Is the sound like this okay? Okay. If anything, just tell us and we will fix it. Okay, so thanks for coming to this lecture. When will robots starting over at Matfyz? Matfyz is here at our faculty. And this lecture will be presented to you by Dr. Petr Čermák, who studied physics here at our faculty and is right now working in the Department of Condensed Matter Physics on several projects. And relevant to the topic of this lecture, he will also be teaching a new subject here at Charles University, the automation in physics, which is also very close to what this lecture will be about. So please welcome Dr. Petr Čermák.
Thank you very much for introduction, and I'm happy to be here, happy that I can present you some of my ideas, but actually I will be also looking for your ideas regarding this topic, and as was said, we will be discussing if or when the machines or robots or some automation will take over our job as a physicist. Just to state, I'm an experimental physicist, so what I will be telling you today, it's related much more to experimental physics than to some theoretical physics, for example. Actually, this question, which is here in the title, like in general, it's not new. So let's maybe start with some very brief, not physical, but overall historical overview, because people were very often afraid that some machines will take over their jobs. And actually this process, this is always connected with something which is called Industrial Revolution, and there were several of them. And first was already a very long time ago, around year 1750 or 60, and there basically became an idea that people don't need to use their own power, but you can use power from the nature to run the machines, and that will help you to do better fabrics, and you can of course do much more fabrics. And people were afraid that it will be done automatically and they will lose their job. Actually, it did not happen, and actually it opened much more new positions. Another industrial revolution, this was connected with basically creation of the lines, which creates also the cars, but also it was introduction to electricity, and this also changed the whole industry a lot. And next, it happened quite recently, like 50 years ago, where basically the computers became available, and they got very much more smaller than before, and we have some CPUs, and nowadays it's part of our daily life. We have all smartphones, laptops, and so on. Currently, it's discussed in industry, fourth industrial revolution, which is not connected with the computers so much anymore, but it's the whole automatization as a process when the whole factory is driven basically by itself. We have already some big warehouses and storage rooms where some robots or some machines which are moving boxes from one side of the hall to another side, they are basically moving independently, and no one programmed them what to do. They are learning from the mistakes, they are optimizing their trajectories, and so on. Actually, this all is related to the industry. People were always afraid that it will take their job, but it happened something opposite, like much more new positions became available. And of course, people did it because it was very, let's say, beneficial for them. But it was never discussed in the content of the physics, of the science, because of course it helped us, like the creation of the computers, this helped a lot, and nowadays it's possible something which was definitely not possible in experimental physics like 60 years ago. Without computers, you need to count on the paper, and nowadays you can count terabytes of the data in seconds, and it's not such a big deal to analyze this data also. So all these came to, let's say, science a little bit later, but it always helped us. But now, with the came of, like, say, artificial intelligence and machine learning, people are starting to discuss if also, like, the science and the work of experimental physicists is in danger, let's say. If you read the abstract of my talk today, I put some reference to the article, which is like a year ago, and it was published in Science Robotics. It was they ranked basically the different job positions, and they put some number how much these people should be aware of automatization and so on. And why I'm telling it, because the job of the physicist was on the top of the list in terms that we don't need to be worried about that. Like really, from all of the jobs which exist at all, the physicists are the best choice actually for the future. So I'm like surprised that there is not thousands of people asking to study physics. So there were a lot of reactions to it, and of course I will not judge this particular paper. It's finally done by some physicists, so it's a question how much we can trust it. But it's definitely a good, I think, time to start asking if it could be, if some of our job at least could be taken over by some robots, by some automation. Because to be honest, not all parts of the job which I'm doing is, like, say, is not boring. Some things are, let's say, repeating. Some things some things are worth of automation. So actually, in order to tackle this question, we should first make clear what's the job of the physicist, because this is not clear, and I realize that different people has different opinion on this question. So I want to introduce some kind of crowdfunding there, and I would like to ask you, what do you think is the job of experimental physicist? If you want to think of my, let's say, time when I'm in work, which is like, I don't know, 6 to 12 hours a day, which part in, let's say, percentage, what I'm doing basically? Do you have any ideas? Yes? So I'm doing, it's experimental physics. I'm studying condensed matter physics. In particular, I'm focused on the magnetism, some correlated systems, correlations between the movement of the electrons and atoms. All it's really basic research. So we are basically growing some crystals, we are analyzing them, measuring by various methods, analyzing data and so on. So, please. Yes, optimization of current systems. So thinking how to improve, thinking how to improve our, let's say, workflow. So improving processes. Some other ideas we are doing, yes? Yeah, it's like reading the papers and learning, or checking. So performing experiments to check some theoretical predictions. Yeah. Okay. To check theory. Some other ideas? Yes. Maybe not just, to find maybe new phenomena or something like that. I mean, that's for sure true. Yes? Discover new states of matter? Yes, sure. I guess we can put it into the same point. That's definitely one of our goals, yes? Okay, it's a good point. Sometimes this is very nice, but yes. Check previous. Let's say results. Okay, despite of performing experiments, you think we are doing something else? Yeah. Yeah, so basically data analysis, if I can like somehow broader summarize it. Definitely. Oops. Something else? Publishing results or writing papers. Yeah. Okay, something else? Yes, definitely. I will say building instruments. Or improving. That's all? Something else you think? Yeah? Definitely. There's a big part of like discussion also between other physicists and it's somehow dissemination of your research, definitely. Discussing and presenting. Okay, something else? I think it's pretty everything. I miss drinking coffee, is still there. She's not related so much. Of course, we are trying to think if robots can replace us, so let's try to figure out if some artificial question? Applying for money, yes, definitely. That's a good point. Ask for money. True. So actually, I was also surprised surprised and interested in this question. So I was like let's try to find out what some large language models think on it. So actually, if I asked the idea of the newest ChatGPT, yes, this is for. But the answer is like similar in 3.5. Anyway, I think it's pretty similar to what you suggested. Of course, we can highly dispute maybe some percentages, but I guess this brings us some general ideas what of really different kinds of jobs we are doing, because some of them are really different. And if I go point by point, I will try to discuss some of them, and I will show you some examples where some automatization is already replacing us or improving our workflows. And the first thing which I will focus, so in this talk, we will focus on like designing the instruments. This is here the number 5. Then conducting experiments, of course, performing experiments, it's important, and the data analysis. There was no space to discuss if especially large language models can write papers for us and publish the results. Yes, it was already tried. It's possible. It's a question if it's a good idea to do that. But I will not discuss that because for me it's really a small portion of some automatization. It helps a lot. specifically for writing the grants. It's a great tool because you need to produce a lot of big amount of text, which has not so much meaning finally. So that's a great tool for that. But I will really try to tackle these ideas because that are finally the kind of jobs which we are spending a lot of time. Very often also students need to spend a lot of time with performing some experiments, and it's not, let's say, ideal usage of their free time. So first will be the data analysis, and now we will come really to the physics, because I will show you the real examples. I will always try to explain you just in a brief the idea what the research is about. I'm not sure about the level of your background, so please feel free to stop me at any point and ask the questions if you don't understand or if I'm talking too long time about something. So this compound here, this rod, this is some perovskite compound where is the magnetic ion is praseodymium, which you can see in the chemical formula. And this creates very interesting properties. This perovskite structure is known to exhibit a lot of interesting phenomena, and specifically these compounds where we have doping between calcium and strontium is very interesting because it's on the border of conducting and non-conducting or semiconducting material. And in addition, it has some giant, let's say, magnetocaloric effect. So if you put some heat to the compound, it can really absorb a lot and changes its magnetic state. So the magnetic state is really crucial for the properties of this material. And if you are studying magnetic, let's say, state of the material, you very often want to look what is happening really when you cool down material to theoretically absolute zero, to 0 Kelvin temperature. Because this is called the ground state. This is basically the state of the material if there will be no thermal fluctuations, how the material will theoretically behave. Of course, we cannot reach the temperature, but we can go very, very nearby, and this will then define the physics, because from the state it's much easier also from the point of the theories to realize what is happening and why we have such properties if we have non-zero temperatures. This is a much easier approach. And physicists, and especially theoretical physicists, studied the system a lot and then created two models how the magnetic ground state of this compound could look like. Now I will simplify it a lot. Let's say you can look like the ground, the magnetism, and it's quite complex now, and we are still figuring out new states of matter based on how the magnetic moments in the atoms are, let's say, stacked, how they are oriented to each other. And you see, it was like measured how the magnetic moments look like in the material. So this was clear. You see that we have here it's just some visualization of the magnetic moment, and we have some arrows, the blue one which goes down, and the red one which goes up. And you see that these two models are the same. So the static of the model is the same. This was known. But in order to realize, okay, why we have this static order in the compound, we need to know something about the forces, because this is caused by the dynamics, by the forces in between of these, let's say, arrows on this diagram. And there were two predictions how it could behave, and they are actually very similar, but have very huge consequences for the real application and for the, let's say, understanding the ground state of this material. So one is based that this was, let's say, simple model, which actually for this compound was very complicated, but this was calculating that the atom, that each of this, let's say, magnetic moment, each of this arrow is interacting with the neighboring atom, and you can look on based on the distance that you have different exchange interactions. These are these J, F1, F2, F3, and they have some sizes, and because of the particular, let's say, particular ratio between these J's, it forms exactly this ground state. But some people say that this is unlikely and created much more difficult model where these always two neighboring magnetic moments are connected to some kind of dimers, and then these dimers interact basically within each other as the whole dimer. So of course, it's some big simplification, but just for now, it's important to know, look, there were two theoretical predictions. And it was exactly this point where theorists ask us as experimentalists, look, you should test which of these theories is true. And these two models are very similar. And it was not very easy to find out the experimental method which could figure out which of these models is correct. And finally, it was possible to use the inelastic neutron scattering. Neutron scattering is, let's say, very rare source, very rare probe for our materials, because in order to have neutrons, you need to have either spallation source, which are very, let's say, costly, or you need to have a nuclear reactor, and of course they are also very, very limited. Nowadays in Europe we have 5 neutron sources which could measure something like that, and actually the signal here was very weak, so I will say that there are like 2 or maximum 3 instruments in Europe who could really measure this physics. But actually it was done, and in this paper they measured this inelastic neutron spectra on a machine which is called time of flight. You put the sample, actually it was this sample, they put it inside of the cryostat, they cooled it down, it was in the neutron beam, and the neutrons hit the sample. There are some energy levels, some allowed energy levels in the material, and they have some momentum, and this is connected, and based on the momentum of these allowed states, the neutrons changed their trajectories, and then they were detected by the 2D detector around. And by all of that, we are counting also time. And by counting that time when the neutron hit the target, we can learn something about the energy of the neutron, which finally was scattered from the sample. So together it took like 1 week, and it was collected roughly 30 million of values. And then people, like the physicists who did the experiment, were clever enough to cut this big space of the 30 million of values to some areas where they expect some differences between these two models. And they really figured out that if you measure on this energy at this particular momentum transfer, you should be able to see the splitting of the band or not the splitting of the band. And they figured out that based on that, this first model is correct. So this is a classical approach. And in order to do it, you need to be, let's say, clever enough, because analyzing 30 millions of values is like almost like impossible without some further knowledge of the problem. You need to have some feeling, you need to have some like direct insight into the problem. But actually after that came another group and say, oh, this is very like difficult problem, and let's try to tackle it via the neural networks. So you want basically to learn your computers how this particular about this particular physics, and then you want that your neural network will decide which of these models is correct. This sounds like a simple question because you are deciding just by 2 options, and maybe if you heard or know something about the neural network, this is usually very like easy to just categorize things to 2 categories. But the problem is that we have these 50 millions of the values which we measured, and it's really difficult to figure out because there is a lot of noise, a lot of other, this is not clear which data are important for us. So in order to do that, they somehow compress the data, but like extremely compress the data. So here you see these 50 millions of values compressed to 1 picture. This is the whole experiment, which took 1 week. They compressed, they cutted this 4D space to some layers on different energies, and then they created these colorful maps. Yes, please. No. This maybe it will be more clear. The method is a time of flight neutron scattering. So the point we are really tackling on different we are tackling which excitations, which is like particular momentum transfer in the system, can contribute on which energies to our final spectra. So this is basically telling us on the phonon vibrations, on the magnon vibrations in the system, on on basically anything what is possible to excite in the system. It will be much more complex to explain you that. I just want to use it as an example how we can, like, how the neural networks can tackle that, because finally all this big amount of values, finally they cut it out, of these 30 million of values were reduced to the image of the size like 400 to 200 pixels. So this is this image. This is experimental image, like whole of this week of measurement is here hidden. And actually, like as a physicist or as a normal, someone who will look on the, you lost almost everything. You don't see the details. This is like a garbage. You can't like distinguish between the branches. You don't see all the energy levels. It's basically compressed, absolutely over-compressed. Normally you will say it's not possible to solve it. But then they created, because all these models are parametric, so you cannot just create, oh, with this model it will look like that, or with the other model it will look like that. There are some free parameters. So you need to calculate a lot of different possibilities, how will it look like for this or either the second model. And they did that, and they generated over 6,000 of such images with different parameters for both of these models. And this they used as a learning data for the neural network. It took a long time. It was a big cluster, and it took like several weeks on this cluster, so it's not a simple job. But at the end, it's important to say, so based on this really compressed image, where like nobody can really see what is happening because everything is like scaled down. This is like if you will take a photo of this room from, I don't know, 5 kilometers far away and try to distinguish the people there, you will say it's not possible. So they did something similar here, but it was clear, and the percentage was, I think, some 85%, that this model is correct. The point is that with this solution, we have no idea why. Actually, we can even question it, because like it seems that from this image, no one can like solve the bands in the material. But by carefully analyzing, and there are some clever ways how to subtract the noise in the data and so on, it was possible to distinguish which model is correct. This is very difficult to apply for, let's say, complex system, and we are very far away of telling, look, I have some data, I have some clever neural network, now what is the correct model for the data? This was only possible because we have two really specific models for the data. In the reality, it's not like that. Like there can be like hundreds or thousands of different models, and very often we don't know the model either. We are measuring something and there are no theories for it. So this is just to show you how far we are and how much computing power we need to use to tackle that problem. And it was possible to use it by just having the insight and measuring correctly. The group was able to solve the problem without any additional problems. So it is possible to use the neural networks for the data analysis, but if you will use it really as a brute force, it's really, really tricky. And it is not scaling up. So it can be used on very only specific scenarios. Next example is by conducting experiments. When I was talking about that I'm experimental physicist on the condensed matter physics, I very often need to prepare some samples, or some of my colleagues need to prepare the samples. We are very often using single crystals because a lot of new emerging materials are highly anisotropic. They have different properties in different crystallographic directions. And therefore, we need to create our samples in the form that the whole sample is a single crystalline sample. We have various furnaces for that. So these are all pictures from our lab, which is here and also in the center of Prague in Karlov. And how does our work there looks like? Typically, it takes 1 day till 1 week until you prepare for the growth of the crystals. You need to carefully check all the starting ingredients, all the elements which you will mix. Then you very often heat them up together, and then when it is heated, then you can use some technique of the single crystal growth to grow the crystals, either from the melt or from some flux, which you can see that you can create crystals, for example, from very salty water, you can create crystals of salt. So something like that we can use also for the metals. So there are different methods, I will not speak about them, and there is a plenty of parameters which we need to play with. There is a speed of growth, we can rotate some kind of crucibles, we can change here, this is heated by the current, here it is heated magnetically, we are creating some magnetic field inside. Here this is heated by the lasers. So there are really different techniques, and all these techniques have very specific parameters, and we need to figure out which of the parameters are correct. Our goal is often has the biggest crystal, or sometimes we don't care about how big is the crystal, but we want that our crystals has no, let's say, vacations or some other errors. So of course it will be great if we can automatize this process, and of course the physicists are thinking about some automatic sample growth. Now it's really small scale, but I think this area of physics is really evolving a lot. To my knowledge, this is the first ever fully autonomous growth of the crystals. Actually, these crystals are very small. They are nanotubes. You can see how small they are. So this is 50 nanometers, 50 micrometers. So this is this tube is mainly done from the carbon. And the way how they are grown is that you have some vapor system there. There are some carbon atoms, and there is some substrate, and you are defining where these nanotubes will grow by pointing the laser exactly at the spot where you want your nanotube to be grown. This is possible. There is a very precise optics, and we can define several parameters. So we can play with the size of the spots, with the power of the laser, and so on. And this all has some impact on the quality of these nanotubes, on the size of the nanotubes, and so on. And for different applications, we want to have a bigger tubes, smaller tubes, with a bigger diameter and smaller diameter, and so on. But this was known, and by that you can program your laser to grow, I don't know, hundreds of the nanotubes in this way. But actually what is new is that we have immediate, by using the same laser light, so this is a really brilliant idea, by using the same laser light, which is then going back from the sample, it goes to, it's called inverted microscope, and then it goes to the spectrometer, and we can realize how big nanotube is growing, immediately. This is called in situ method. So immediately by using this power of the laser, and this spot of the laser, we can see always these parameters. The nanotube has these parameters. It's multi-parameter problem. It's not clear to realize how to do it automatically. But the trick which was used here is used by some. Sorry, that should be in English. Anyway, I will translate it for you. It's used Bayesian optimization. This is it's one type of closed loop techniques, which is one technique from machine learning. And the idea is that you have some multi-parameter problem, so you have some multi-dimensional space, and you expect that for some set of these input parameters, you will have some output which you can measure. And this output could be, for example, quality or size of your nanoparticles. So you want to say that you want the biggest nanoparticles for sure, and you want to optimize your process to have the biggest nanoparticles. So by doing that, you will select some set of parameters, then you will conduct the measurement. And why it is called closed loop? Because then you will measure the results, and then you can, let's say, improve your, at the beginning, your multidimensional space is somehow blind. You have no idea which parameters produce which results. So you go somewhere and you produce some results, And then by that, the machine is learning, oh, okay, this was not so good. Let's try some different parameters. And by doing that, it will learn, okay, this is like better result. And then this technique is trying to approximate and realize what will be the optimal parameters. I think it's the best could be seen on the animation from the calculation from the system, how it evolves. So here on this, just focus on this top chart, it's still going in the loop. But the point is by each measurement, you have some, what is here in the purple, this shaded area, this is your possible uncertainty. So these are where this violet area, this purple area is the biggest. There you have the biggest probability that this is basically the region with most unknown results. And the parameter has some clever approximation techniques, which tells him, oh, this is exactly the place where I have no idea if it will be like good result or bad result. So this is a good place for the next measurement. So by applying this mathematics and statistics, basically, this system can learn itself, but not only learn itself, but it can optimize the amount of measurements. So normally, of course, you can do the same if you will, for example, scan the whole this multi-dimensional parameter space. You can realize the points where is the maximum. So of course this you can do, but this will take a very long time. But by this system, you can by the order of magnitude minimize the amount of needed measurements, and you can realize where will be the next measurement point. Just to see the outcome, how long it takes. So this is the experiment number, and every experiment number took, I think, like half an hour. So they were performing a lot of gross experiments, and the whole machine was learning itself. It was learning not only how to and it has different tasks, different goals. So the point is that even if the goal is changing, so for example, the goal could be that the particle needs to be, I don't know, highest. And then they change the goal that the particles needs to be whatever, purest or biggest at all. But the system at the beginning was still learning how to adjust the parameters, so you see that every another experiment was really different. But after running some time, it crossed, let's say, the region, and there is some mathematical calculations which tell you, okay, now with like we are in the region where we will not measure in the wrong positions at all. So this black curve is always like the ideal goal. This shows us where we should how we should set our parameters. And you see that after like 500 experiments, the whole machine learns itself how even by if you change the goal, if you change the task, you can very quickly accommodate, and you don't have the spread of the, let's say, wrongly set parameters at the beginning. So this is, we are not speaking yet about any neural networks. This is, but it's a machine learning technique actually, and it's used a lot. It's not used only in the sample growth. It's used also for example, the robots, these walking robots are using the same techniques to learn how to not fall down, for example, because you don't have so many tries. If you like fall down, you don't want to fall down million times. This is different from the neural networks, which can really try and try and try and learn on a big amount of tries how to solve the problem. Here, you don't want to perform it, let's say, million times, and you want to really here, you just want to have it like 500 times, and it was really multi-parameter space, and then you are able to learn what's the best technique. This technique is used, for example, also for searching for the places where it's good to dig in the earth to find an oil, for example. So the technique is really very powerful, and it started to be used in the laboratories by the physicists. In industry, it was, of course, used a long time ago. The similar problem which we are tackling is that sometimes when we are measuring, the measurement is takes a long time, and a lot of like running such instrument is very costly. So I already have spoken before how we can use the neutron scattering. And if you want to use that, as I said, there are like really 5 places in Europe. The nearest is in Germany, another source is in Switzerland, another in France. And in these sources, you can ask for the measurement time, for the beam time, and you will get, for example, 3 days of the beam time, and you need to use it as much as possible, because it's easily cost 1 day of running the experiment costs like millions of euro. So you want really to optimize your measurement technique, and you don't want to measure the noise. And this is an example of this data, so I will not explain the physics here anymore. But this is some excitation, and here is our 2D space where we can like search. And let's imagine that measuring 1 point in this 2D space takes, let's say, 10 minutes. And you together has time to measure 400 points. And now it's up to you to choose which points to measure. And of course, you have no idea that this is the result. This is how it looks like in like the theory. You don't know that. So you need to somehow realize how to measure. And in the past, very often what was done that, okay, I have 4 days, you will divide this space to the grid and you will measure on each point. This is like normal approach, you don't need to think about it. Okay, you need to calculate you need to divide some numbers, but this is very simple calculation. And then you will set some machine to measure in these points. And this was done when I was a student. I was using this technique exactly to search for the excitation. But actually you can use the same technique as before. It's called this Bayesian optimization and usage of some Gaussian processes. And it can basically, you will use, at the beginning, you will measure randomly somewhere just to find out the places where are the intensities. And then the algorithm will choose the places nearby these intensities to measure more. So you can see that this is a whole theoretical approach. So in theory, it will be much better to measure just here and not like that, because you will have much nicer picture of this theoretical work. And here, these are the results from the real experiment, where it was really the material which we have no idea what is there. So there is missing these theoretical predictions. But here we use this, let's say, stupid method of just using the grid. And here we use the same amount of points, but the algorithm was deciding by itself where to measure. So we used same time, but the quality of the data is like not comparable. For example, here we fully missed the region here, where is something interesting. This region is not enough measured. Here we have much more ideas, and actually here we see that this excitation continues here in this direction, and so on, and so on. And the point is that this could be, of course, done by some clever physicist sitting there. The experiment is running all the time. It's all running during the night. And if you want to use your time wisely, you can sit there, or your team can sit there and decide, oh, just measure these 3 points, then you will wait half an hour, then decide, okay, this looks promising, let's measure around. But this takes a lot of time. And we don't want to spend 4 days, but full 4 days, like 24 hours a day, sitting there by the machine and deciding where to measure. But you can see that the machine can in a clever way, decide by itself where to measure. And it's actually much more complex inside, because the machine also calculates the time from going to one point to another and optimizing these times of movement and so on. And the last example which I will show you is what we are doing in my team in the lab here. Actually, the robot which I will show you is in the center of Prague, in the laboratories of Karlov. And we are tackling the problem, and I'm again back to these neutrons, because this is somehow my field of specialization. Very often we are not able to have big enough crystals to measure some interesting physics. And the neutrons are very rare, and it's difficult to get very strong signal from our measurement. So what we can do, we can co-align more crystals together. This is not like our idea. I tried to search the literature, and first people who co-aligned 2 crystals was this Hutchings and Samuelson. They aligned 2 crystals together to get better results. What does it mean they co-aligned the crystals? I told you before that we are using a single crystal, so they have some crystallographic axis, all these samples. And if I will orient them like together, but not precisely in the same crystallographic directions, my results, because the results are very anisotropic, my results will be blurred or even completely meaningless. So in order to measure the signal on more samples together, these samples need to be somehow stacked or glued together in a very specific way that I need to first determine what are their crystallographic directions and glue them like in the same way. This technique is nowadays used a lot. People are co-aligning a lot of these crystals, and it takes a tremendous amount of time. This is the example from the paper from 2019. 2 years later, it was reached. This is like the world record up to now published. Over 2,000 of the crystals is co-aligned. What does it mean? Every of these 2,200 crystals you need to put to the diffractometer, determine its crystallographic directions. Then you put this mark. You see there are all the blue marks, blue lines on the samples. And then you will work under the microscope, and you will glue them as close as possible to this plate. Actually, I'm communicating with this group. They are really good in co-aligning the crystals. And recently, they reached to co-align over 10,000 of the crystals. This was work of 2 students for 3 months, like the only co-aligning the crystals. This is like horrible, and you don't want to do that. And you want to have a machine which will do it for you. That's, I think, clear. So the machine is here. The machines we are developing on the faculty. It's very simple. It has a robotic arm. It has an X-ray source. And it uses the lower diffraction, so-called, to figure out this crystallographic axis, and then glue the samples together. So the original idea is very simple. You take the crystal, you put it to the lower beam, you then somehow analyze the results, and you glue it to the plate. Of course, in the reality, it's much more complicated. You need to tell the robot to do it. So this is not like telling the students, let's do that. You need to somehow program the robot or teach them. The robot needs to be connected with some cameras and so on. We are using several industrial cameras to determine the initial position of the single crystals which are laying on the plate. Is very easy, finally. Then there are libraries for that already, so this is not difficult, which can defect edges and so on. For grabbing the crystals, we are using suction system, so this is sub-millimeter crystal, which we can like grab and use it for the alignment. It's used, it uses like a vacuum cleaner. It basically sucks the air, and by that, it can pick the samples. We have very precise robotic arm. It's the smallest industrial robotic arm in the world, and what is very nice that it's extremely precise. It has repeatability of 5 micrometers. It has distance like 30 centimeters, but if it's on one position, I do some complex movement, I can then go back and I will be in the original position plus minus 5 micrometers, which is ideal for our use case. Then we are using commercial Laue diffractometer, so it uses X-rays, and this X-rays is basically shining on the sample, and then we see these spots, and this is actually the reciprocal space. This is Fourier transform of the real space where are sitting the atoms in the lattice of our crystals. And by analysis of these patterns, for analysis we are using several methods. We are currently determining which method is the best. Most of our methods are using neural networks, but there are different approaches. Either they are like feed-forward neural networks, which can really take the image and tell you, oh, this is this orientation. Or we are using some reinforced learning, which is a different approach. I basically tell the artificial intelligence to move my robot in the position that my crystallographic A-axis will be, for example, in this direction. So this is more approach like which is used for example, playing the video games and so on. So it's a game for the neural network to solve my goal as best as possible. And we are also using some other techniques how to solve it automatically. We have several very precise cameras. So this is the shape. The size of this crystal is a little bit below 1 millimeter, and we can have very exact shape. And this is needed because finally we are calculating, we have some clever algorithm, which is kind of bin packing problem, which is calculating where exactly to put the crystal in order to save the space. So it's like playing a puzzle, but you have no idea what will be the next piece. So of course with a puzzle it will be like not possible. You cannot solve the puzzle without putting the pieces back. But of course there are holes in between, but our algorithm is trying to minimize them, and it's performing much better than the physicists are. They are aligning it by eye and hand. So our algorithm is comparable to the commercial algorithms. Commercial algorithms are not so powerful because they know the shape of all the crystals, let's say before. This is used for cutting the fabrics, for example, when you want to optimize the waste in the companies. But we don't know the size and of the crystals because we are grabbing them one by one and then we want to glue them automatically in order to speed up the process. Together, I will not speak into the details. It has several computers which are talking together. Some of them are using neural networks, and overall system is using this closed loop optimization, which I told you before. So basically, we have really different and distinct algorithms for aligning of the whole machine, then counting where are the crystals. Then we are solving these Laue patterns in order to determine the direction of the crystals. And at the end, we are calculating where to place them. Also, placing the crystal is not so simple. We need to play with the amount of the glue, for example, which we used, because sometimes the sample a little bit rotates when we glue them. This all is not possible to optimize if you use it by hand. So you have no idea which force you used. If you use the tweezers to glue something somewhere, you don't know the parameters which you used for gluing the sample. But with, if you use the machine, you can, of course, parameterize everything. So you know the force which we applied to the sample. We know exactly the amount of glue which was used before below the sample, and so on. And all these parameters, here it is correct. Here the diagram is in English. We use this Bayesian optimization process, and our machine is, let's say, co-aligning 10 crystals with these parameters. Then it's gluing the crystals, but putting a little bit more glue. Then it's putting the crystals, but it's using different distance where it basically drops the sample to the substrate, and so on. And at the end, it can create like 10 different groups of crystals which are glued by different parameters. Then we put this big plate, and we analyze them, and we can evaluate what was the best technique used. And these parameters we used for this closed loop as a new loop. We will evaluate them, and we will put them as the new initial parameters. So after this took like a week, and after a week, we improve our algorithm, and the next time the algorithm knows, oh, look, this was the very promising, but I should maybe a little bit play with this parameter because there could be some further improvements. And this is all working like automatically. Actually, we have no idea why it is choosing these parameters, but we are like sure, and there is also some mathematical background and statistical background that we are sure that it's correct prediction. So my talk is almost over, and I will be open to the questions from the audience. In order to summarize my talk, I think there are still some areas where there is really no way that some machine learning or AI will replace us. Of course, you can write to ChatGPT, I'm a physicist, what should I do? And it will like write you something, but this is not, this is just compilation of the text which already existed on internet. So of course you can do something. This is very often what people are doing in physics. You can read the paper and you can, oh look, this is very interesting work. I have similar compound or something, I will do exactly the same thing. So of course this is possible. But if you want to discover something new, it's not possible just to copy the work of the others. So there needs to be some kind of invention, and with that, there is no way that some model or some machine, at least like nowadays, will help you. Of course, with discussion of colleagues, drinking coffee, and so on. There is a lot of parts of our job which we are enjoying, and this we will enjoy still, even if there are the robots and the neural networks everywhere. And it's really a question if it will be better if I will not be standing there, but there will be some automated machine and doing some funny presentation automatically, because it can learn from all other already given talks and compile it the best talk ever, and then we can have a machine which is doing the best lecture of mechanics, and all the people will look to the same machine, because this is, let's say, optimized talk. So this is of course possible. I think we are in theory not far from it, but it's a question if this is something which we will at the end enjoy or not. On the other hand, I hope I showed you some examples where we could be really replaced, but of course by some automation. But of course it's a question first if it's a good or bad thing. I think it's really good to, for example, if the machine will co-align the crystals for us, because no one wants to sit 3 months in the lab and just stack the crystals together. And of course, a lot of these, especially like in the data analysis, a lot of these methods are really limited. What is, I think, some take-home message for you, that this field is really evolving a lot. At the beginning, I was thinking to put some neural networks topics there more, but I realized that for like 1 hour talk, I will not be able to be so broad in the topic. And it's very difficult topic at the end. I think a lot of physicists are now used to know some programming, but the knowledge how the deep neural networks works, this requires really a lot of effort. And the point is that it's evolving a lot. If you know how the deep learning was working a year ago and you did not follow the trends, after 1 year you are almost lost, because there are new algorithms, new approaches. A lot of these approaches, it's not known why they are working. It's just known that, look, it is working. It's also related to well-known GPT. It's not known why it is working like that. We just know it makes sense. A lot of text makes sense. But it was no one like had idea, look, it will work like that. A lot of people tried before. They had different parameters, different layers, and it never produced such, let's say, clever results. So this field will be for sure evolving a lot, and knowledge in the terms of specifically this deep learning, where you have a lot of layers of different neural networks connected to each other. This is really something for the future, and I suggest to everyone not to study the physics, but also to join at least some lectures on informatics and try to learn as much as possible from machine learning. And with this, wait for it. I thank you for your attention. Actually, maybe just before, I'm a big fan of the Marvel movies, and there is always some post-credit scene, so I prepared one post-credit slide after it. The machine which I showed you, this robotic device, this is called ALSA, like Automatic Lower Sample Aligner. Which is somehow developed. We are using it and it works pretty well. But what we are using it now, we upgraded the ALSA, and we are now thinking to create the whole automatic process for the whole laboratory. So our team is now growing. we are setting up some spin-off company on Charles University, and I hope in the future we will be able to produce some small autonomous laboratories, which will be really focused on the tasks which are mainly boring and for the physicist to conduct. And okay, this is the real end of my talk.
Okay, thank you very much. Thank you very much for a great lecture and for the journey through automation. And now, if there are any questions, I think we could take a few questions. While they are thinking, I will ask. I was wondering, it touches upon what you said at the end about how the trends are going forward and how it's not very easy to actually learn all that is needed to do this automation. And you are obviously using a lot of different automation methods just for your work. So I was wondering if you are also cooperating, for example, with the computer science department or other departments, or is it more like, let's say, a bunch of physicists that are learning AI and with the knowledge of the experiments and just applying them, or what's the approach?
It's an excellent question. It's difficult because all this process is just at the beginning, and we were, like, as a physicist, we were not used to communicate so much with the people from informatics because it was really like distinguished directions, and to do some script which will automatize, I don't know, go there, measure this, go to the another point, count here 5 minutes, then apply this current to your sample and so on. This was easy and everyone can do scripting. You don't need to ask people from informatics to do that. Nowadays, we are in the situation where we need to communicate. And of course, it's not, very often it's not easy. I will say it's very similar to the problem of communication also between the theoretical physicist and the experimental physicist, because there we are, it's also a little bit separated words, but in order to produce a good results, we need to collaborate and we need to find, let's say, the same language, because the theoretical physicists don't see our problems with the quality of the sample. Their sample is always the ideal sample. Our samples has problems, there are some vacancies, there are some problems. It's the same with the neural networks. So if you study really the theory of the deep learning, you focus on some very simplified topics like, okay, I have some data set of the numbers and or faces, and I need to distinguish between them. But our problem is very often very difficult to explain. It's not like, okay, look, everyone can say this is a cat or this is a dog, and this is actually a great example for improving the neural networks. But to distinguish between two models of some magnetic ground state, this is not so simple to explain someone who does not understand the physics so much. So this is really the topic where we need physicists who also understand like both words. And I think it's much higher chance that some physicists will learn at least partially the neural networks than some people from informatics will learn some part of quantum physics, because this sounds much more like a sci-fi.
Okay, thank you. Thank you very much. Okay, do we have any other questions regarding the lecture or the broader work? I will give you the microphone so it's recorded.
You say that discussions with colleagues cannot be automated, but could something like an AI be up to date with all the new research and fields and helping the problem you mentioned about miscommunications and people focusing on different problems?
It's, I think, to a very limited way. So I'm personally using it. We are, for the communication in our department, we are using Slack. So there is like 60 people on our Slack channels discussing with each other. There are some common rooms, and I have no time to follow all these rooms. There is a robot, sidekick robot, which can summarize, and if I go there after vacation, it writes me, okay, people were discussing this, and these people ask you these questions, and it creates my to-do list. So this is great. But it is not asking if you can turn some, let's say, experimental mode, and then this AI could try to ask the questions in the chat, and this is fully like nonsense. Like, it makes not so much sense. So it's not the valid partner for discussion. Sometimes you can use it, but this is also not working, because like following up all the papers, it's really takes some time. So you can ask the AI to do the summary, but it's not picking the correct, like, I will use it differently, and I force my students to pick different points which things they are important. So basically, but I think this could improve really rapidly, and maybe in like few years it will change fully, and it can be really partner for discussion at least, or it can oppose your ideas. But nowadays we are not there yet. But I'm somehow looking forward. It will be fun.
Thank you.